Hey, welcome to section 6.3. We're going to start studying exponential functions. All right, so exponential functions arise from something that we call proportional growth or change. And we'll get into what that means in a couple minutes. So first, we're going to motivate how this is different from what we've usually done by first talking about additive growth. So suppose you work a job and you make, let's say, $200 a day. Actually, let's do 100. That's probably more realistic for a college student working a part-time job. And you make $100 a day. All right, how much do you make after 1 day, 2 days, and then some number of n days? This should be pretty easy for all of us. We know 1 day, obviously, we made 100. So if we're trying to find a function that models this, we might say that f of 1 is 100. The next day, we've done 2 days of work. So f of 2 is the amount we've made on 2 days, which is 100 plus 100. And so that's 200. On the nth day, we've worked 100. We've earned 100 plus 100 n times. And so that gets us 100 to the n. All right, so this model is telling us that to find how much we made when we're adding, we just need to do a simple multiplication. What's a little bit harder is this proportional growth or exponential growth. So we did a problem in class where we were talking about how much would you make on the nth day if on the first day, if on day 1, you made $1, day 2, you made $2, day 3, you made $4, and so on. So it keeps doubling. So now it has this proportional growth factor where you're going to grow in an amount based on the amount you had the day before. We know how much we make on day n if we know how much we made on day n minus 1. So it has this relation that f of n equals twice what we made the day before. And we just keep carrying this out so that f of n minus 1 goes to 2 times f of n minus 2. And we can pull this whole chain of equalities down until we get 2 to the n minus 1 f of how much we made on the first day, which is $1. So that's just 2 to the n minus 1. So instead of a multiplication, we get an exponentiation to model how this is growing. So when we have these proportional increases, So we're growing based on the size that we have the day before. We end up using exponentials to model that. All right, so let's do another example with exponentials. So also in class, we talked about a COVID model, and now we're going to talk about exponential decay. And this is going to be, this time we're going to talk about when people can also be removed. In our case, we'll just say they're no longer infectious. So we'll have the same setup. We have some population P, 1,000 infected on day 1. Each day a person infected has a 1 in 20 chance of infecting someone. So that's our infecting rate. And now we're going to add that our infectious period is 4 days. Now, this setup is not exactly what COVID is. You know, people think that you're infectious for COVID for 10 to 14 days. Choosing 4 in this example will make the numbers work out nicely. Otherwise, I would do 14. But if you want to be more realistic, you can just follow along, and anywhere you see a 4, just replace that with a 14. Okay, so we'll call I1 the number infected on day 1, and that's 1,000. So let's ask what I2 is. So how many people are going to be infected on the next day? Well, we suppose we have this baseline 1,000. So those are the people already infected. Of those 1,000, 1 in 20 are going to infect someone else. So we'll have some growth there. But also on this day, a whole bunch of people are going to heal or become non-infectious. So we assume you only have a 4-day infectious period. So it's a safe assumption to think that 1/4 of all the people will not be infectious the next day. So this is our baseline. This is new infections. And this is newly non-infectious. So what this is, the way this kind of works though, is that you start off the first day with 1,000 infected. And on that first day, they've gone around and infected people, but the new infections aren't counted until the next day begins. And then once that next day begins, we also assume all these people are newly non-infectious. Right, so we can kind of simplify this down and see that we can factor out 1,000, and then we get 1 plus 1/20 minus 1/4, which equals 1,000 times 16/20, or 1,000 times 3/4. Okay, so this is showing that our rate of growth that we're going to have is going to end up being 3/4. So on the next day, we have 3/4 as many people infected as we did the day before. And it turns out on IN, we would have I times n minus 1 people infected times 3/4 by a similar computation to above. And then just like we were doing before, we could say that that's I n minus 2 times 3/4 times 3/4, which is I n minus 2 times 3/4 squared. And we carry that down all the way down to I1 3/4 to the n minus 1, which is 1,000 3/4 to the n minus 1. Okay, now a really incredible thing happens when this number is less than 1. Turns out that if that number is less than 1, our IN has n behavior 0. And that's because when you multiply fractions together, they get smaller. So 3/4, then the next one in the sequence is 3/4 squared, which is 9/16. Then 3/4 cubed, which is 27 over 64. So we started out at 3/4, which is about 75%, to 9/16, which is slightly over 1/2, to 27 over 64, which is less than 1/2. And you can just keep carrying this on. 3/4 to the 4th is 81 over 64 times 4, which is 128,256, which is less than 1/3. And we keep continuing this. And so that actually tells us that the number we have infected on day n, it keeps getting closer and closer to 0, which means that the virus is going to go away. So this is one way that people can model what kind of implementations should be taken. If you have something that's moderately infectious, then you just need to put in enough measures so that way it won't be too infectious. We just want to get this number below 1 and it'll go to 0. And then we can be saved. Rather than if it was greater than 1, it would go up to the whole population, up to infinity. I guess while we're doing this, it'd be good to conclude by writing down what this function actually, write down the formal of the function. So IN, that's the number infectious on day n, is 1,000 3 to the 4th n minus 1. All right, I hope you enjoyed this video. We'll have a couple more on exponentials, and then we'll be moving into logarithms. All right, see ya.